Hello everyone, my name is Timotée Ly-Manson from IMT Atlantic, and today I will be presenting our latest work in collaboration with Sony Stuttgart Research Center titled Analyzing Few-Shot Neural Architecture Search in a Metric-Driven Framework. The goal of neural architecture search is to find the best neural network architecture in the search space for a given task. In this work, we explore the few-shot NAS line of work, where the search space is iteratively split into several subspaces. Our main contribution is the formulation of a framework to split the space in a tree-like fashion using any network evaluation metric. We leverage zero-cost proxies as part of our framework and use our benchmark experiments to make several key observations about few-shot neural architecture search. In this presentation, I will first lay some background elements, then explain our method. Finally, I will detail our benchmark experiments and the key takeaways. So, as for one-shot neural architecture search, which is one of the most popular paradigms in NAS, it follows a simple pipeline. First, the supernet is trained, then the candidate architectures are sampled and evaluated with the help of the supernet performance as a proxy. Generally, the supernet is defined in a cell-like manner, such as in the widespread NAS Bench 201 search space, where each cell defines a directed acyclic graph, which contains all of the operations in the search space. However, as far back as 2019, the one-shot approach was criticized due to the inability of the supernet to rank architectures in the right order locally. This issue has been linked to the weights of every candidate architecture being shared inside the supernet, leading to bad optimization, an issue which came to be known as weight sharing. Few-shot neural architecture search was introduced to reduce the impact of weight sharing. The few-shot NAS paradigm is a middle ground between a one-shot neural architecture search with a single training and vanilla neural architecture search with exhaustive evaluation of all the candidates. The search space is divided into several sub-supernets, each with reduced weight sharing compared to the whole supernet. The question is then, how to find the best split of the search space into a given number of sub-supernets? Several methods have been proposed to do so. In the seminal paper Few-Shot Neural Architecture Search, the search space is split exhaustively with respect to each edge. Another idea later introduced is to group operations together in sub-supernets based on how similarly they behave during training. As such, GMNAS proposes to compute the pairwise similarity of the operation gradients and constructs a binary tree of supernets by separating operations into two groups of highest similarity. When leaving out the gradient similarity part, the GMNAS method defines a framework to generate splitting trees of sub-supernets from any network evaluation metric. Taking inspiration from this method, we extend the framework to work with any arbitrary metric. When splitting with respect to an edge, the operations present on the edge are evaluated one by one using the chosen metric. They are then compared against each other by way of their pairwise distance. Finally, the most similar operations can be grouped together via a main cut optimization problem. Zero-cost proxies have attracted a lot of attention recently in the NAS community as low-cost estimators for network performance. Various proxies have been proposed in recent times. A simple one counts the number of parameters in the network, while others leverage metrics from the pruning literature or take advantage of the neural tangent kernel. We leverage the representational power of zero-cost proxies to obtain the full pipeline of our method. The trained supernet is split into a number of leaf sub-supernets using zero-cost proxies, then a one-shot-like algorithm is applied to each to obtain n candidate architectures. We benchmark our method with 9 zero-cost proxies and 4 one-shot algorithms over 3 datasets: Cypher 10, Cypher 100, and ImageNet 16. Our first observation is that in every case, splitting the supernet produces better results than keeping the full supernet, showing the effectiveness of the few-shot NAS paradigm. However, no one proxy produces the best split consistently across all algorithms and datasets. This seems to indicate that the benefits of the method rely more on the splitting itself than the metric used to split. Further, by leveraging the tabulated NAS Bench 201 space, we display the distribution of architecture accuracies inside each split. Our visualization represents a search space split into 8 parts. On the x-axis, we have the ground truth validation accuracy according to the benchmark. On the y-axis is the distribution of the architectures. The union of all 8 distributions would amount to the full search space. We observe that architectures are homogeneously spread amongst all subsubunits, while the most beneficial outcome would be for all good architectures to be grouped in a single split. By zooming in on the top 1% of architectures, we continue to observe that the best architectures are spread in multiple subsubunits rather than isolated in their own subspace. The key takeaway of this observation is that in most cases, it cannot be said clearly that one subsubunit is the best, as they all contain good architectures. This is an important observation because of a pipeline adjustment that most few-shot-NAS papers make. Let us come back at the few-shot-NAS pipeline. Before applying the downstream search algorithm, all few-shot-NAS methods append another step to the pipeline, the selection of a subsubunit using an ad hoc criterion, such as the validation accuracy of the subsubunit. In order to evaluate the effectiveness of such criterion, we look at the training phase of each subsubunit. On the y-axis, we plot the performance of the found architecture at each epoch. The selected subsubunit based on the validation accuracy criterion is represented with a red marker. We observe that the best subsubunit is not selected at convergence. Therefore, the criterion is suboptimal. Moreover, when applying successive halving as proposed in GMNAS to discard lesser subsubunits early and reduce the cost of training, we observe that the best subsubunit is discarded early, which is undesirable. As a result, validation accuracy is not a good criterion to select the subsubunit. In summary of our work, our experiments give insight into various key elements of few-shot neural architecture search. First, splitting the search space into several pieces always produced better results than one-shot NAS in our experiments. Secondly, we were not able to find a metric that is superior to any other to predict these splits. So it is likely that by itself, the reduction in size of the search space is responsible for most of the good results of few-shot neural architecture search. Thirdly, the distribution of architectures is disadvantageous and disrupts the notion of there being a best subsubunit in any given split. Finally, we showed that the most commonly used criterion to select the best subsubunit, that is validation accuracy, is inadequate. Overall, our work shows that while few-shot neural architecture search is a promising development in NAS, it requires more careful tuning than what previous methods have surmised. If you are interested in our work, come see us at the poster session of the AUTOML conference or contact one of the corresponding authors via mail.